Next we have Jeremy Voix doing acoustical and geometrical properties of custom earplugs obtained with an automated fitting system.
Thank you, Laura. Good afternoon. So I'm Jeremy Voix. I am now an associate professor at the University of Quebec, and Cédric Bacon is my master degree student. So he's the Canadian student that did the work. Edin is the Iranian postdoc that did the statistics, and I'm the Frenchman that takes the credit. So what I will present today is really a study that we did on the results obtained with an automated fitting system. And I was actually part of that engineering effort that took place at Sonomax while I was the CTO up to 2010. But this project really belongs to a university project which is under the umbrella of the Sonomax ETS Industrial Research Chair in in-ear technologies. So just to give you an outline of what will be discussed here, I will just present you first the needs that actually the issue that we're faced with the Sonomax technology at that time. The research that has been conducted. I'll present you the data analysis that we just did, and some of the conclusions and maybe future possibilities. So to really understand where this comes from, I think we have to go back a little bit into the time, and probably in the 90s, and especially in 92, with a fellow that most of you do know, Professor John Casale, and that patented in 92 a custom fitting earplug formed in situ using foaming action. And the idea here in that patent was really to have a kind of bladder inside the ear canal that would be inflated and that would conform to the ear canal using some kind of foaming magic. Well, the problem with this magic is that it eventually never worked really, and so we just at Sonomax stole the idea, and a few years later came, actually in 2001, exactly at that place, NHCA 2001, we came with that idea of injecting a medical silicone-grade compound inside the ear canal. So the idea would be to have, again, an earplug that has that membrane, and within that membrane to inject a two-part silicone that would cure and give you a solid earpiece in a few minutes. So the idea looks good, promising, and was implemented using what we called technicians, so trained technicians that would be trained to do that injection. And obviously that requires some dexterity and good hand coordination, because that was still a little tricky process to know exactly when should I stop injecting that earplug, for example. That was one big question. So the outcome of that uncertainty is that we had actually a few issues concerning what I call repeatability and reproducibility. So repeatability is the idea, well, if I'm asking a trained technician to do that subject, that worker, to do that ear impression over and over and over and over, what kind of results do I get? Do the earplugs look exactly the same? Are they different or not? So that's really what we call repeatability. And reproducibility is the idea, well, this technician is good, but what about this one? Is he able to get the same kind of yield and good results? So that was necessarily a concern I had as an engineer. But just for the corporation point of view, there was a bigger issue. That issue was really the scalability. Having to send a technician on site was apparently gaining a lot of time, because in 3 minutes you had a custom earplug, or 5 minutes rather than a 3-week delivery process and so on. One of the problems is, well, when you have a few thousand people to do, how do you really scale that up? That technician will be working for days and weeks, and that can be a little issue too. So this is really what drove actually the study and the results that I'm presenting today. And now I think you really understand the needs. The needs were really to be able to design a system that would take care and replace basically the technician. So this is obviously a very solid engineering exercise that has been conducted in 2009 by Sonomax team, and I was still part of that team at the time. And the criteria, the design criteria we had were really that this system should be scalable. You understood why. So we thought, well, if the person could fit themselves, that would be perfectly scalable. We could just take that off the peg, and here we go. So self-fitted was the first requirement. The other one would be that it would be reliable. Anybody could do it without any hand dexterity, any knowledge, anything. So that would be to automate that system. Obviously, we needed that system to be inexpensive, so forget about smart ideas of having microprocessors, captors, electronic, that would be mechanical. And I can add, there will be an easy to use, so that would be a one-button thing, so that anybody can do it, and a long shelf life, and I can add and add and add, you know how engineers do work. But really what was my interest were 3 research questions. Those 3 research questions were, well, when should I stop that injection, you know? And how would I stop that injection? And finally, what kind of reliability would I get out of that system? So that was really how we started that research exercise. And the research that we conducted was obviously to go back to some basics. So the basics was at first to really understand how an earplug would be inflated and how that would expand in the ear. So we took the injection gun that you saw and instrumented it to measure exactly the volume that was injected and the pressure that was built up. So here you should recognize on the right-hand side the earplug, which is here orange, and you see the yellow part, which is a silicone that would flow inside that earplug, and the rest is just the electronic that does the acquisition of the volume and pressure. And looking at ear inflation in various configurations, we got those results. So those results are nice to look at, but I can maybe just give you the underlying idea. If you want to know when to stop injecting or inflating a membrane in the ear canal, you will quickly discover that there is a very basic physical property, is that if I'm inflating that balloon here in the open air, if I was to measure the volume, you would see the volume increasing, but the pressure wouldn't build up much, right? Because the envelope is so thin that you have what we call a quasi-isobaric extension. Now, let's say that I'm inflating that, but now inside an ear canal or some kind of constraint, guess what? The pressure will build up. So the idea was, and this is really the second rising curve that you do have, so you see the pressure in blue and the volume in green. And you see that there is a nice match. We can find a sweet spot that corresponds to a good inflation. Why? Because the earplug did touch the ear canal and had a pushback from the walls. So that's the idea. So now we knew when to stop. The question was, well, how would we stop? And here's the concept that we got of this self-fit. And this is really the little illustration of how we would stop this inflation. So this is the little animation. And you will see the silicone, the pink silicone, flowing upwards, if you can see it, outside of the syringe, and reaching eventually the earpiece. And inside the earpiece, you will see that pink silicone expanding the membrane in order to conform to the ear canal. And obviously here the volume increases and the pressure builds up. And eventually what will happen is that the pressure release that you can see here being activated will release the pressure. So you now have a perfect expansion of the envelope against the ear canal. That should eventually cure. That was our hope, and you should get a perfect product. So we had to try that. And that's our next step. That was really the proof of concept. And so obviously, this always starts with a very good-looking applicator system. And so here you recognize again in yellow the silicone flow, part A, part B. Here the earplug is orange, that's on the left-hand side. And here the electronic to monitor. We had pressure, we had vacuum, we had speed, we had temperature, we had a lot of instrumentation. And we had to move to human testing. So human testing was 5 minutes after on a human subject, as you can see. And really here, this is the kind of work environment I really enjoy. This is really the kind of teaming between industry and academics. So you can see a PhD student that is fitting actually the current VP of R&D at Sonomax. And really, I enjoy that kind of teamwork. But here in that case, I don't know if Michael Chocot was enjoying that much. Not too sure what that eyesight was, concerned being toasted by the electrical circuit or bursted by the silicone. So anyway, to make the story short, that took quite a few work from this R&D team to actually finalize the pump as a very self-sustainable or self-contained system that is that size that I now have to validate. So how would I validate that this does the work? Well, I would certainly try to repeat fitting the earplug over and over on the same subject and see how it goes in terms of attenuation, that's the feature, and in terms of shape. So let's see how I did that. I did that by obviously scanning the self-fitted custom earpiece. So to do that, we start obviously by injecting the earpiece. So this is how the pump is held over the head. And this is one of the test subjects in the lab. And we do repeat that measurement. We did that measurement 26 times, so 13 times each ear. And you do then go to what we call a CNC machine that does scan very precisely the shape, the outer shape of the earplug. That could be with contact, so this is a little stinger, or that could be here simply with a laser. So you see the laser beam that will be scanning that orange earplug here. Then after a lot of processing and merging and image consolidation and so on, you get what we call the 3D scan. That's simple. And just to give you a little idea, this is how the 3D scan of the earplug looks like. And from that, this is exactly that shape that we are gonna that we will now analyze in our experimental data analysis. So the earplugs, as I said, were taken in 26 times. So those are the earplugs, that you get out of this injection molding process. That was the very first time that we tried that one. So it has since evolved and improved, but that was the raw results we got. And there will be three things I'll be measuring. I'll be measuring the mass, I'll be measuring the attenuation, and I'll be measuring the geometry. So the mass, if I look at the results, you see here what we call the normal probability plots of the 13 earpiece masses. And you see that they do align quite nicely on a normal distribution curve, and they do fit very tightly. So the standard deviation is less than 0.05 grams. So that was quite the same volume that was dispensed, except maybe for one outlier, number 3 in the lower left corner. And we'll see that number 3 item later on. So that was looking, quite reasonable. And when we looked at the attenuation, that was quite easy to do because obviously we could use an F-Mario system, so measuring outside noise, inside noise, and measuring really the earplug attenuation using the Sonopass system that Sonomax had for their earplugs. And here, if we look at the standard deviation of the PAR, so PAR for the personal attention rating, we see that we have quite a tight distribution as well, with a 1 dB standard deviation. And 1 dB, may look a little bit large, but there is some measurement uncertainty and some placement uncertainty. So that was reasonably good agreement, except for 2 outliers. Now number 3 again, and now a number 1 that you see in the lower left corner. Now let's go to the geometrical aspect. So the geometry, that's a little bit more complex because you have to realize that an ear plug, an ear canal, that's a free-form geometry, as we call it. This is not a cylinder, this is not a cone, this is nothing we know. This is really a free form, a free shape. So one thing you have to find is what we call the centroid. So that's really that orange curve that goes in the middle of every cross-section. But to find that middle of the cross-section, that's quite an iterative process. And you have here a few equations just to impress you, but really the idea was to get the numerical placement of those center points. And so again, this is how we define those, and this is a classical approach that we adapted, but that are available for free-form geometry with binomial vectors. And what I just wanted to say here is that we'll define not only the cross-sectional area, so how large is the ear canal, but we'll define 2 other metrics, which are the curvature, so this is how it torques, and the torsion, so this is how it changes planes. So those are mathematically defined, and I don't bug you with this, but they are known functions that we can clearly derive from the center curve. So here, just because I told you that it was an iterative process, this is when you start the process, this is what the MATLAB script will give you, a very bad slicing of the earplug that doesn't look very accurate to my eyes. But if you run the process 20 times, this is finally what you get. So a very nice, smooth, distribution of the cross-section. And now that we have those geometry, let's do some math. And the math is really to plot here as a function of the distance. So be careful, 0 is the inside tip of the earplug, and you see the cross section on the top level. So you see this is the very thin part that is inside the earplug, so the distal end, And then as we increase the x-axis, we are going outside of the ear canal. So the diameter obviously increases, as we understood. So from 6 to 10 millimeters in that case. You see the shape at every instant. And what you see on the graph below is the curvature. So you should recognize, if you're familiar with what we call second bend, first bend, you see them very clearly in that case. They are mathematically defined, very clearly identified here at 6 millimeters and 14 millimeters. And just to give you an idea where the first bend occurs, that's really at the entrance of the ear canal. The second bend is really a little bit more deeper. And you see here what we call the torsion that occurs, that's the bottom graph, that occurs really in between the second bend and the first bend. The reason is because we are changing plane. So that's the process we do for one earplug, and we have 26. So the aggregate results are those three curves. So you see the diameter that was the cross-section area that was changing for those 13 earplugs, and you see the kind of distribution we got. So you see that for the diameter, you see that for the curvature, and for the torsion. And what you may see as well is that the number 3 that was really underweighted, that was too light, is clearly underfilled. So it's the smallest one, it's very thin, not properly extended. And you may see here in orange that the number 1 that was not giving us a very good attenuation is actually not very large in the ear canal portion where it matters. So we have now good hints of why we had those bad attenuation results. They were just not properly filled. So, out of those curves, I should do some math. And the math I did take, the standard deviation at every point. I did aggregate that standard deviation across all the points, and I did, shake that, and I got a number, and that number is the APOS of 3.7. So that's the value we get out of that. That's the accuracy of my measurement system, of that manufacturing process. The problem is that it's a number, and there are 2 problems with this number. First, I made up the number. And the reason I made it up is because I can compute it any way I want. I can do exactly what I described to you, which is actually the way I would have done, and I did. But there are many ways we could compute, well, how reliable is that size, how variable is that size, so standard deviation, distance to mean. We can do a lot of stats. The problem is that nobody does that stat. So there is nobody that did it. So, well, I'll define one that's called APOS, but that was my first problem. There was no method to do it. The second one is that, well, 3.7, that's a good number, according to me, but I don't have anything to compare to. Well, why? Because nobody published that data, and there's no benchmark to be used. So that was the issue with the APOS. But we'll see what it means exactly in a few minutes. Well, we'll see it now, because I'm going now to present you my conclusions. And the conclusions are threefold. The first one is, I think that I demonstrated here that mass customization, which are really 2 words that do not fit usually together, is possible. And the reason it's possible is that because we have now, Sonomax has now a custom earpiece that is not a hearing protector, it's really for entertainment purposes, so it's an earphone, and that is commercially available, so that is possible. And I measured the reproducibility of the dispensing system, and we show that the APOS value was 3.7, which is quite good. So, as for this is my only product placement here, but I'm really proud that Sonomax launched that product and got actually a few weeks ago the Best of Innovation Award at the CES, so that tells you that there is some traction going behind this. Thank you for them. And this really, the second point is really important for me, and I think it really rings with what was presented with Scott. I think there is really now a need for rating those custom products. And I would really go for a custom ear mode quality rating, because I think that there is a need for a metric that will evaluate how reliable your molding process is, and I think Scott did a great job at explaining how wide those processes could be. But there should be a metric to be done, because at the end, you need the performance. And I will just share a very true history. When I started in that business, so in 2001, I got my very first custom earplugs, and they were made by a very established North American company. And at the same time, I was developing that field attenuation measurement system for my PhD, and I could not get any attention out of the right ear, and I was really concerned by my measurement system. But later on, I realized that that was a leaky custom earplug that I got on my right ear, and that was my very first experience, pricey experience with the custom molding process. So I think we should even push a little bit further, and I think a standard would be really appropriate to allow, comparison between ear mold quality, and you may have needs for hearing protection, huge, great quality. You may just need consumer products. You may have different, there is a range for everybody, but that's to protect the customer and to ultimately save our ears. And the metric I would then propose is really the APOS, and APOS is actually a very long acronym because that's the aggregate of pooled standard deviation of cross-sectional area, curvature, and torsion among multiple refits of a custom molding process on several subjects. But that's my proposed indicator. So I think the last statement is a little bit of a forward-looking statement, and I'm not a fortune teller. I don't have all Laura's talent. But, when I was here 10 years ago, I guess my spiel was that, fit testing will eventually make its way, and it's not completely crazy that we could test individually on a regular basis and so on. And I think this is getting traction, and we saw that just from the talk from Gulfstream. And so I really believe that inflating membranes, as I call them, are here to stay. So if I'm really looking into my tea leaves, apparently this is how you call that, look into the future, and I think this is the right place in your lane to look at that. I see some, and I can recognize when technology are promising, and I see a very interesting web page, Lantos Technologies, with here a fellow that we know here from NHCA, but certainly a very interesting conforming membrane that inflates, expands to the ear canal, and actually scan the ear canal. So I think this is, just another proof that you should really watch for those expanding membranes. Thank you very much.
I think we have time for a couple of questions. What? Thank you.
What kind of program did you use for the slide transition?
Well, I think it has nothing to do with the software. That's really the skills of the presenter.
What about somebody would have a bunch of wax, or possibly if you're doing it for consumers and nobody's examining the ear first, is there a danger that you might be pushing something into the eardrum?
No, that's a very good take. This is exactly the reason why this consumer product is quite shallow. As you could see from the 3D rotation I gave you, this is a shallow fit, exactly to avoid to have an otoscopic examination. But I think Sunmax, is looking at those, coming back into this industrial business protection, hearing protection business, and in which case otoscopic examinations are required. Absolutely right. I agree with you.
Following on to that, how difficult would it be to adapt to military application, or would we be definitely looking to go deeper?
Well, we at Sunmax, that was always the next step was always to go deeper and deeper, and I think this conforming membrane is not something that Sunmax master quite well, but and I think they have plans along those lines, but I'm no longer there, and I cannot really answer as for their plans. Sorry.
I'm afraid we're about out of time here, so thank you very much.
Thank you.